Hello everyone. Today we are going to be talking about a very foundational paper in our foundational series, continuing our foundational series on artificial intelligence. Welcome to ARC session number 5, where we are going over learning representations by back-propagating errors. This is a paper from 1986, and this paper has been written by Rumelhart and McClelland. This is also one of the most foundational, I think, one of the more important foundational papers, which goes over parallel distributed processing and exploring, and the formal title is Explorations in the Microstructure of Cognition. Um, in this paper, like they are essentially going over processes that would later be known as that would later become to uh, be called the phenomena of back propagation, where we essentially take an inaccuracy in our current model's behavior, and then we go back and backtrack and then correct that mistake. It has changed a lot of how model design is done, and it's not just something that people should know, but is very much relevant if someone intends to work in the sphere of model development and engineering architectures for creating more advanced neural nets. Today, we are very excited to have this specific paper, because this lecture is about one of those rare moments in science where a single paper was able to bring about a fundamental architecture change. As I said before, we are talking about the learning representations by backprop errors, which was published in 1986 by Dr. David Rumelhart, Geoffrey Hinton, and Ronald Williams. Geoffrey Hinton, as we all know, is also the father of modern artificial intelligence. Um, this paper was able to do something very remarkable. It looked at neural networks from the graveyard of failed ideas and turned them into the engine of modern AI. If you have ever had the chance to use facial recognition, or gotten recommendations from Netflix, maybe asked Siri a question, all of that traces their roots back to this 1986 breakthrough. Um, I can not say that you will understand all of the math behind it by the end of this talk, but I can promise that by the end of this hour and a half of a conversation that we are having, you'll understand back propagation not just as a collection of equations, but as a genuine breakthrough in how we teach machines how to learn. We will be building from intuition into mathematics, and I'll sprinkle in some real examples that can show how this algorithm actually works. We'll be covering four main things today. First is going to be the historical context, where we'll discuss why this problem mattered and why people had given up on neural networks, which was the AI winter. We went over this in our previous ARC session, number 4. Um, the core algorithm, that is something we'll be going over, which describes how backpropagation actually works in a step-by-step manner. We'll be giving some real examples in our third section, where we will talk about how a network that learns to detect symmetry, and we'll also be talking about another that understands family trees. And finally, we'll learn about the impact, which is how did this 1986 paper lead to everything we call deep learning today. Think of this as a guided rescue mission. If neural networks have ever felt like you're drowning in math, I'm here to see how we can catch ourselves up to backpropagation and become standing on solid ground again. So, without further ado, let's start with the first section of our talk, which is the problem. thinking about the rise and fall of the perceptron that we were talking about in our last meeting, picture the late 1950s, where Frank Rosenblatt had just invented the perceptron, a machine that could learn to classify patterns. It was simple, it was elegant, and it worked. Newspapers called it the thinking machine as it could learn, right? But then, 1969, in 1969, two researchers named Marvin Minsky and Seymour Papert published a book called The Perceptrons, and in it, they had shown something devastating. The perceptron couldn't solve certain problems. One of these problems was the XOR, which is the exclusive OR. XOR is a logic gate. It outputs true if its inputs differ and false if they are the same. Mathematically speaking, input 0 0 gives an output 0, input 0 1 gives a 1, output 1 0 gives a 1, and input 1 1 gives an output of 0. We also went over this with the decision matrix that we drew last time. Um, Here, the question arose that XOR cannot be solved by a single layer neural network. It's impossible to do so. And Minsky and Papert proved it mathematically. We went over this mathematic in our ARC session 4. The impact of this paper, it was drying up funding, and funding eventually did dry up. Researchers moved on to other approaches. Neural networks fell into what people call the AI winter, a decades long period where nobody wanted to fund this research. But there was a nagging question here. Why couldn't perceptrons solve X, OR, right? Like, why wasn't it able to work on the XOR problem? The solution that seemed impossible, and we went over this last time, is you can solve XOR if you add a hidden layer, an intermediate layer of neurons between the input and output. And let's go over that like solution one more time in a more simple like fashion so that we can reinforce. Think about it geometrically in one dimension or two dimensions. XOR is not linearly separable if we plot the points. But if you transform it into a higher dimensional space in which a hidden layer is present, and this is what a hidden layer essentially does, then suddenly it becomes separable. A single layer network can't do that transformation, but a multi-layer network can. So researchers had a hypothesis in the 1970s and 80s. If one layer isn't enough, then why not just add another here? The problem was that nobody knew how to train a multi-layer network. There was the credit assignment problem, where this problem essentially gets a little more interesting. Imagine that you're a teacher grading a multi step math problem and the final answer is wrong. You want to figure out which steps were wrong so you can give feedback to them, right? If a student had only had one step, then it's easy. The step is wrong and they can fix it. But if there are five steps and the final answer is wrong, which steps caused the problem? How much blame does each step in this problem actually deserve? So, how do you grade it? This is a credit assignment problem, and it was the central challenge of neural networks. In a single layer perceptron, you can easily tell when an output is wrong because there is just one layer and you can look at it.
You don't know where it went wrong.
Yeah, but in a multi-layer network, the hidden units don't have a target that you specify. You only know that the output is wrong. So how do you adjust the weights of the hidden layer is essentially the problem. For decades, there was not really any good answers to this, and that's why neural networks were pretty stagnated because, do you see the black box that everyone
Yeah.
is talking about? This is the black box. And that was the gap that Rumelhart, Hinton, and Williams filled in 1986. Now we can go into part two of understanding what these neural networks actually are, and it reinforces the analogy that we were just making. Before we get to the final like solution here, let's make sure that we understand what a multi-layer neural network actually is. The architecture is simple. Imagine a feed-forward neural network. It has layers of nodes, i.e., neurons, that are arranged in columns. So there's an input layer, there's a hidden layer, and there's output layer. Say input layer like is a 8 unit thing, and hidden layers are 5 units, and the output layer is like 1 unit, because that's where all of the output essentially ends up aggregating. Um, each node in one layer connects to nodes in the next layer, and each connection has a weight. Think of it as an adjustable knob that controls the strength of the connection. So there's an input layer, there's the hidden layers, and then there's the output layer, and they are all connected by these connections that have weights which can be ideally thought of as knobs that can be adjusted, and these knobs are going to be the intensity of how these connections are. Similarly, thinking in your neurological system where there are dendrites and there's axons, and an impulse when fired is essentially a function of what was the intensity of this impulse, and what is the threshold that this impulse needs to cross in order to cause an excitation in the neuron itself. There's also the factor of how long it's traveling and what is the thickness of the dendrite, because these are things that will essentially govern how far and with what intensity an impulse can be fired. This also ties into the fact that people have tolerances to certain things, and these tolerances are affected by these factors as well. The length of the synapse, the density of the synapse, the length of the neuron that it's traveling through, and also what is the threshold that needs to be crossed. Whenever someone says that I'm a thick skinned person, it means that the threshold that you need to cross to cause an impulse is going to be a little more. So that is what these tunings are supposed to be doing. Each neuron does something very simple. So now we are getting into how a neuron actually works. Is each neuron does something very simple. The it take For starters, it takes the weighted sum of all of the inputs that it receives, and say like we have a neuron J that receives the signals y1 and y2 from the previous layer, weighted by which is the intensity w1 and w2. So now it will compute the weighted sum here, meaning that the external variable that is attached with every dependent variable that we have, it just multiplies it with it, so it gets a weighted output, and then it sums all of them together to calculate whether this is good enough for the impulse to be fired or not. So essentially, if a neuron J receives signals y1 and y2 from the previous layer, weighted by the weights w1 and w2 respectively, then it computes xj, which will be equal to the sum of these different components, which are y1 w1, y2 w2, y3 w3, yn wn. So multiplication and all of the sums. Second step, it applies a non-linear activation function to these. A non-linear activation function. The most common one in 1986 was the sigmoid function, which was yj. So remember, xj was the sum we calculated, and this weighted function which will be applied is going to be yj equals 1 over, remember this, 1 plus e to the power minus xj. Right? We went over this math last time. This is the non-linear activation function which is applied to this weighted sum. Okay. This squashes the output between 0 and 1. So once you apply this, it creates a probabilistic, which is going to be between 0 and 1. And based on that, our decision is taken. And this like function is essentially an S-shaped function, hence it's called a sigmoid. That's it. Each neuron is doing something very simple, a very simple math, which is a weighted sum, and then squeeze it through a curve. Squeeze it through a curve as in trying to fit it between 0 and 1 here. That's what this sigmoid function is doing. Because the composition of the linear functions is still linear, you have 10 layers, but each just does y equals x. The whole thing is equivalent to y equals x. You haven't gained any power here. But the sigmoid is non-linear. So even though each layer is simple, when you stack them on top of each other, each layer can distort and transform the data in more complex ways. Multiple layers of nonlinearity will give us real power here. The weights are the learning parameters. As we went over this just now, the weights, think of them like knobs. They can be treated as learning parameters. And here's the key insight. The network is defined by its weights. When a company is trying to steal trade secrets from you in the domain of AI, what they are actually trying to do is get your one.txt file, which contains all of the weights that you have.
Yeah.
Now, these are going to be like, have you heard of a 1 billion parameter model, right?
Yeah.
What are these? What are these like 1 billion parameters, right? These are the 1 billion weights that have been adjusted by training and classifying and inferencing and then benchmarking your model. Based on that, you adjust your weight so that you get the most accurate output predictions that you want, right?
Yeah.
So essentially, the hidden layers are where, like, this magic actually happens. Now, like we said before, uh, the network is defined definitely by its weights. The training procedure doesn't change the network architecture; it just changes the weights of this architecture. Think of each weight as a tuning knob. Learning means finding the right settings for all those knobs so that the network produces correct outputs. Correct is a subjective thing. It's like the desired output that we want. So we bend it to the will that we want. If I say that I want a model that can write anything that I want in Pig Latin, then I want to be training a model that only, bends towards the rules of Pig Latin. So it bends itself to the kind of output that I deem like desirable. So here it's not going to be correct output, is it's going to be like the output that we desire from it. And it can be anything. We can train it to do anything we want. And then let's think about why these hidden layers are actually so special, right? Like these sigmoid hidden layers. The hidden layers are where this magic actually happens. The input layer and the output layer are kind of boring, because we know what this is. They are just data and predictions. But the hidden layers, this is the actual feature learner where these weights are adjusted. The hidden units can learn to represent anything useful. They might learn to detect symmetry or edges or concepts like nationality, as we'll see in a later example. This is radically different from the perceptron, where all features had to be handcrafted by human beings. Let's dive into like our third part now of the discussion, which is forward and backward. When I was talking about this earlier, you must have noticed that I proposed a forward thinking architecture when I initially started with the example. Here, in this section, we'll be able to get to the heart of the algorithm that we are discussing, which is backpropagation. Backpropagation has two main phases. One is the forward pass, which is making a prediction. This is the easy part. You take a training example, say an 8-bit pattern for the symmetry detection task, you clamp it to the input layer, and then the signal flows forward. Remember the architecture that we had discussed, like input, middle, and output,
Yeah.
right? Oh, yeah. Okay, so we talk about input, the network that it goes through for the weight training, and then the prediction part. So, like I said, this is like the easy part. We take an 8-bit pattern to form a symmetry detection task, we clamp it to the input layer, and then the signal flows forward through it. Hidden layer 1 here computes its outputs based on the input weights. And say we have another hidden layer that computes its outputs based on hidden layer 1's outputs. So it passes through first layer, a computation is done, passed through second layer that uses that to compute another computation, and then the output layer gets this compute and it outputs it based on everything before it. The result is the network's prediction. Clear? For example, if the network is trying to detect symmetry and you give it the pattern 100110001, that is 10011001, the network might output something like 0.87, meaning that I'm pretty confident that this is symmetric. Like if you ask the question, is this symmetric, after like training it on a symmetry detection, it'll say I'm pretty confident that this is symmetric. You also have the target output. Although, like, I believe that this could be trained like using a binary classifier where you can just have an algorithm and it can, with 100% certainty, just predict if it's if not even predict, just see if it's symmetric or not, and like give you, like, that was a non-efficient example. But say, like, you train a model for some reason that can tell you if something is symmetric or not based on prediction, the vibes, I guess. It might output something like 0.87, meaning, I'm pretty confident that this is symmetric. You also have the target output. For that pattern, the target is 1. So, this is where it gets interesting. So you have a target pattern, which, like, say a human has labeled based on that algorithm, but you still wanted to learn how to, like, predict. So there's a target which is 1, that, it is symmetric. It's not really that deep. So the error is like going to be E equals half times 0.87 minus 1 square. That is the mean square. Remember, mean square error. So what that is mean half.
Yeah.
Because there's two things that we are dealing with: the prediction and the ground truth, right?
Yeah.
So what you do is prediction minus truth whole square divided by 2, because you're dealing with two things. So this is mean squared error, and that error here comes out to be 0.0085 if it said that it was 0.87 confident that it's a symmetric pattern, right? This is your error for this example. If you repeat this for all training examples, you get a total error. Goal of learning is make the error as small as possible. So this is what you write in your forward pass algorithm. You want to make sure that your error rate and the sum of your all errors is as small as it can possibly be. That's how it adjusts its which we'll get to right now. And the second phase is going to be the backward pass. So we went over forward pass, and this is the backward pass, which is computing gradients. Now comes the brilliant part of the algorithm, where we need to figure out how should each weight change to reduce the error. This is where calculus comes in, specifically the chain rule of calculus. The step one in this backward pass is an output layer error. Start at the end. At the output units, we can directly compare prediction to target. For an output unit J, error signal is prediction minus target times derivation of the activation function. In symbols, we can write this down as yj minus dj times function inverse of f of xj, which is going to be, sorry, function inverse of xj. Xj is the activation function. We are creating the first derivative of this activation function, and then we multiply it by the prediction minus target. We just went over this. For a sigmoid function that we were just talking about, the sigmoid hidden layers, that derivative is yj times 1 minus yj. So you'll see this like in an algorithm that we can, like, write out sometime and create like a learning example that can plot things right in front of us. So we can take that up and create like a script that can help us do that and visualize this a little better. But let's just for now think of it like this. It makes sense intuitively, because if the output is too high, the error signal is positive, which means that we need to turn it down. If the output is too low, because it's a direct multiplication, right? Like if the error is too high, then we multiply it with a bigger number. So the error signal is going to turn out to be positive, right? If it's too low, then we multiply it with a smaller number. So it's going to be negative. And, that means that we need to turn it up a little. If the neuron is saturated, which is it's either going towards like the heavy end of 0 or 1, and the derivative is then the derivative is small, so the signal is going to be weak, and this will be a little hard to change. Great. Let's look at the step 2 here then. After essentially calculating the output layer's error, we need to see what the gradient of each weight is at the output layer. And here's where, it becomes a little more elegant than the last like mathematical crude step. For a weight W connecting unit I to unit J, the what we want to calculate is error signal of J were multiplied by the output of I. Let's see what the nuance is here. So the if we have two neurons getting connected, like we have J and we have I, and I comes first and J comes first and I comes later. How do we, like, map the weight that is supposed to be connecting these two? Like how do we define what intensity these two should be connected with? So what we want to do is we want to calculate the error signal of this times the output of this. So we want to calculate the error signal. So the first pass calculation of like what we just discussed multiplied by whatever the output of this thing was. And that's how we decide what the weight is going to be. What this means to say is the gradient for this weight is proportional to how active the source was and how much error the target had. That's what we want to use to decide the intensity of the connection that they'll have. Now Think of it this way. If the source unit was off, as in the output was 0, it didn't contribute to the output. So don't change its weight much. If the target had a big error signal, blame all the incoming weights. If both are true, then the weight is the thing that will take the hit here. Here, we need to understand how this propagation error that was calculated will be sent back to the hidden layers so that the weight can be adjusted. This is where, this is where we need to understand that if we have hidden units that feed into the output layer, then we can ask a question: what error signal should a hidden unit actually get? Like, it is calculated, but what signal should it be getting to make that to make that change in the weight itself? The answer to this is simple. We sum up the contributions from all of the units that are given to us and the units that it feeds into. So if a hidden unit connects to the outputs of unit 1, 2, and 3, and each of these output units sent back an error signal weighted by the connection strength, then the error is the weighted sum of all of those three signals. I mean, what all of the neurons essentially gave us an error. Yeah. And we want to see what was the total error coming from this, from this set of weights that we had. What we want to do is just sum up all of the errors that we had. That this is what we were talking about even earlier when we wanted to calculate what the error was. Like in the previous paper, what we would do is we would calculate the mean square error. We subtract the calculation that we got, the 0.87, from the ground truth that we know is supposed to be true, which is 1 or 0. We create that difference, we square it, and then we add all of the others together so that we know that, okay, this is the cumulative error that we had. Even in this case, to move it forward from the calculations that we actually made, we want to add those errors up so that a tweak can be made in our original weight. In symbols, this would be recognized as the derivative of this sum multiplied by this step applied to the previous step times the weights that we are actually looking at. Here, the sum is over all units j that the H neuron actually connects to. Once we have this calculation, we can compute gradients for the weights feeding into it exactly the same way. Error signal of this multiplied by output of the source unit. So whenever we are moving forward with every layer, we just want to calculate with one at the back end, and then the calculation applied to it, and then it multiplied by the one that it wants to connect to. So we are just moving in a like straight manner so that we can calculate um, what the synapse or the connecting body has intensity labeled as. So, to calculate or recalculate, if you will, their connection strength, you just look at the error generated and the expected truth, and then doing the mean squared error on it. Then we repeat it all the way to the back. So we keep doing this layer by layer. We keep going backward through the network, and each layer's error signals depend on the layer in front of it, like we just said. Eventually, we have error signals for every neuron. We have gradients for every weight. And an intuitive and I think I can solidify this a little better, skipping the math a little, from an example of a hiker. So imagine that you are lost on a foggy mountain at night, and you want to reach the valley, which is the minimum error. You are at a mountain and you want to reach the valley, and you have fog between you and the valley. So you can't see a lot further, than you would when everything was clear. So you can't really see that far, and you can't just walk around the valley. Instead, you feel the ground beneath your feet to sense which way is downhill, so that you take a small step in that direction. Um, so that you can eventually reach the goal, which is reaching the flat valley. The error surface is your mountain, where the weights are going to be the position that you currently are at. Back propagation is computing the slope, which we refer to as the gradient here, at your current position. So back propagation is computing the slope, the gradient, at your current position. And gradient descent means taking a step downhill. I'll go over these terms just one more time. The error surface is your mountain,
Yeah.
like with respect to a function. The weights here are going to be your position, and back propagation is the activity of back propagation is computing the slope or the gradient at your current position. Current position, what is the slope, right?
Mm.
Gradient descent means taking a step downhill. That is what gradient descent is. So the act of moving from your current position by calculating, which was computing the slope, which is gradient, to go down slowly towards valley, which is your optimum, like, place where you want to be. And you want to reach the valley, which is the minimum error position, as, like, quickly as you can and as, like, efficiently as you can, whatever. But that is like optimizing your algorithm. The error surface is your mountain, the weights are your position, and backprop is computing the slope at your current position. If the slope is steep, you know the downhill direction very strongly, like which direction is downhill at. If it's shallow, which means you're less sure, back propagation gives you that slope for every weight simultaneously. Let's get into the algorithm now. And this is going to be, like, again, very straightforward. Before that, let me take like 1 minute. Okay. I need to plug in my Mac. Is everything that I've said so far making sense?
Yes.
Okay.
Yes. Mm. I can't read, so that's one.
Even I'm noticing that my eyesight is going away.
Yes.
Like it's evaporating now, right? Oh man, I do not like that.
You don't want to get old, scary.
Hmm. Yeah. It does get scary though. Okay. I was just like sitting today and I was looking at my laptop, like in my lap, and I couldn't, like, like, see something. I was like, no, this isn't supposed to be happening to me right now. Okay. Let's get into part four now. The algorithm. Wait, I'll just quickly make another Discord announcement also. I think people can benefit from this. Uh, mm, it's fine. Okay. So now we get into part four, which is the algorithm itself. Let me put all of the things that we have just been discussing together in a training procedure now, okay? This has a few steps to it. Step zero is initializing our weights. Remember the baby that comes with standard things and doesn't know too much and needs to be programmed as it grows up? That we went over, like, maybe in the first arc, I think. Start with small random values for all weights and biases. This is something that, like, I also hear time and again is, if you don't know really what you want and there's something that you can do, maybe just going randomly gives you a good odd of just ending up, like, somewhere. Anyways, like a random example is, like, to me, still a better example than, like, nothing. Why random? Because if all the weights start with zero or the same value, all neurons behave identically. Random initialization breaks that symmetry, allowing for different neurons to learn different features, right? The training loop now. For each training example, we'll repeat this many times. There'll be forward passes. Feed the example through the network, computing activations layer by layer until you reach the output. And we compute the error, the mean squared error, yeah? Yj minus dj ka whole square, halved it, and we create a sum of this. We do a backward pass. Secondly, we compute the error signal for the output units, which is the first derivative of xj multiplied by the error. For each hidden layer, we go backward, we compute the error signal, and for each weight, we calculate the target times source. Now we do the weight update based on this. So the delta is going to be minus nu, the activation function, times derivative of this. Um, and the new weight is added, which is the which will be essentially the old weight plus the delta w that we are calculating. Okay, the new weight is going to be the delta, which is the change in weight that we want, added to the old weight. Okay, this can be both negative and positive. It can be any kind of value. I mean, if it's high, then we need to go get low, and if it's lower than we want the expected to be, then we go higher, right? Not that complicated. Okay. uh, where's the slide? Okay, perfect. Um, hmm. Cool. And then we basically repeat this process. And in this, in this flow that I described, n is the learning rate, which is a small positive number. And we repeat this. We go to the next training example and keep doing this. After many cycles through all training examples called an epoch, that you must have heard of, epochs in training cycles, the error should decrease. Like, hopefully. If you're not, then you're doing something wrong. Keep going for multiple epochs until performance becomes better, which is essentially it fits itself. It either overfits itself, it underfits itself, or it does a good job at fitting itself. The learning rate here, which is a critical hyperparameter, is going to be defined as follows. The learning rate n controls step size.
Yeah.
If it's too large, you overshoot the minimum. The might even increase your error. If it's too small, then training is extremely slow, not nice. Just right. And if it's just right, then the steady progress will be shown until starts going downhill. Okay. You want your learning rate to be be falling in one of these three brackets. In 1986, people used constant learning rates like 0.1 or 0.01, whereas modern methods sometimes start big and decrease over time. Okay. In and in this concept, we also need to think about momentum, which is a helpful trick. The paper mentions momentum here, which is a refinement. Instead of just moving in negative gradient direction, you can carry some momentum from the previous step. There's also a mathematical function of this, which I won't go over right now, but we can have a technical discussion on that also in one of our academia events that we'll be having next semester. This is something that we'll be talking about. A lot of quantum computing, machine learning also deals with this. So I think we'll try to have a talk that incorporates this. It's like a ball rolling down the hill. It doesn't stop at every slope change. It just smooths things out. This helps avoid oscillations and speeds up convergence. When it's rolling down, you know what I mean? It carries momentum with it. Let's go over an example here, right? A real world example. Symmetry detection. Let's see how this actually might work. This is not a real world example. This is a real example that we can understand. Okay. Think of a task, which is we are given an 8-bit input. And we want the network to output 1 if the pattern is a palindrome, which is it reads the same forwards and backwards, and 0 if it's not. Problem clear?
Yes.
Great. Here, what we are going to do is, let's look at some examples. You tell me if it's a palindrome or not.
Okay.
1001, 1001.
Yes.
So what should be the output? 1. Okay. Let's look at this one. 1100, 0011.
Yeah.
Okay. So output should be 1.
Yeah.
Think of this one. 1000, 0001.
That's palindrome.
Yes. And then 1100, 1001.
Not a palindrome.
Okay. So the output is 0, right? This is impossible with a single layer network. Do you know why? Because any single input bit tells you nothing about whether the whole pattern is symmetric or not.
Okay.
Right? I mean, it's an 8-bit string, right?
Yeah.
And I give you the first one, 1.
Yeah.
Can you tell if the whole string is a palindrome? No, because you need to go over it multiple times, right? So if you're on a for loop, what is that?
It goes over it 8 times.
Right?
Yeah.
And that's how it can tell, right? If it's like an 8 character string, it still needs to look at everything. The string by itself doesn't have any identity that says it. You can then calculate it and give it So your neural network can look at it and classify it and then give it a value 1 or 0 based on if it's a palindrome or not, right? Like,
Yeah.
but that is a higher dimension, like work that your brain did to bring this scattered thing into like a structure and then give it like an output label, which was a high dimension, like, job done on things to give it like that label, right?
Yeah.
Like, makes sense, right?
Yeah.
It's not like a high dimension thing that can be looked at like by itself already and have a value associated with it. So this is impossible with a single layer network, because any single input bit tells you nothing about whether the whole pattern is symmetric or not. You need to compare the left half to the right half, right?
Yeah.
So we can solve this problem in like a three-dimensional step, maybe. So like, that's the step that your algorithm will probably do. Like, cut the thing, if it's even, then cut the thing in half.
Mhm.
And then look at the left side and look at the right side. Now, if the broken parts are still even, you need to break it down even further, so that it can, like, look at it. And it can look at it, right? If it's not even still, then it breaks it even further until you reach an odd, in which case your one like will be like, it'll either be a single digit, so you can compare the left and right now, or it's a middle point of something that is still even or odd, right?
Yeah.
And then it looks at that middle and then keeps computing the left equal right or not. So that's how like a palindroming algorithm, like, actually works, right? Like,
Yes.
okay, perfect. You need to compare the left half to the right half, and that's you call a recursive function and all of that, and then you're able to tell if it's a palindrome or not. But the network that they had trained to solve this problem, so Rumelhart and colleagues used a simple network: 8 2 1, 8 inputs, 2 layers, 1
One
output.
output.
Okay, 8 input units, 2 hidden units, 1 output unit. They trained it on all 64 possible 8-bit patterns. It's a small enough problem to enumerate, with a learning rate of 0.1 and a momentum of 0.9. It took about 1425 passes through the training set to learn it perfectly.
Okay.
What the neural network actually learned. This is where it, huh?
What do they use to make?
Perceptron machine.
Like the same thing. So how many of them?
8 inputs, 2 hidden layers, and 1 output layer.
Yeah.
Yeah, that's what they did, right?
Yeah.
Okay. This is where it gets beautiful. After training, the weights had a very specific structure. The 2 hidden units each had weights that were symmetric. And oh, by the way, why 64? Because 2 to the power, yeah, 2 to the power 8 is, no, 2 to the power 6 is 64.
Whatever.
Okay, whatever. The This is where it gets beautiful. After training, the weights had very specific structure. The 2 hidden units each had weights that were which were symmetric and
Yeah.
opposite. Okay. 2 to the power, wait, oh, 8 to the power 2 is 64.
That's also.
That is why it's
Yeah.
64 common, not 2 to the power 8, 8 to the power 2.
Yes.
My bad. That's why I was considering, like, wait, that doesn't make sense. Am I doing something wrong? Okay. The 2 hidden units each had weights that were symmetric and opposite. The 2 hidden units, which each had weights that were symmetric and opposite in this problem. That's what they observed. Their weights were symmetric and opposite to each other. For example, in hidden unit 1, weights from inputs are +1, +2, +4, +8, -8, -4, -2, -1. And the hidden unit 2, weights from inputs that are -1, -2, -4, -8, +8, +4, +2, -1. What does this mean? When you have layer when you have 1 coming from layer 1, then this will give you -1. When you have 2 coming from here, it'll give you -2. When you have 4 coming, it'll give you -4, 8 and -8, -8, 8, minus. It gives you the opposite and equal value, like uh, like, magnitude. Sorry, equal like magnitude, opposite direction.
Yes.
Okay. See the pattern here. If the position is 1, and if the position 1 is +1 and -1, which is opposite. Position 2 is +2 and -2, and so on. How it works? Here's the clever part, which explains why it works. When you present a symmetric pattern like 1001, 1001, hidden unit 1 computes 1 times 1 plus 0 times 2 plus 0 times 4 plus 1 times 8 plus 1 times minus 8 plus 0 times minus 4. These are the weights. So remember 1 0 0 1 1 0 0 1. Remember the weight file that we had? It was 1 2 4 8 minus 8 minus 4 minus 2 minus 1, multiplying each together, right? So 1 times 1, 0 times 2, 0 times 8, sorry, 0 times 4, 1 times 8, 1 times minus 8, 0 times minus 4, 0 times minus 2, 1 times minus 1. Sum all of this together. What is the sum that you're going to get after this?
0.
Exactly. So you get a sum of 0. Hidden unit 1 computes 0, and hidden unit 2 similarly, which is basically the opposite of those weights, also gives a sum of all 0, right? Both hidden units get the net input of 0. With a sigmoid activation and a negative bias, they output near 0. They are off. They are in the off. These output units, the output unit has a positive bias. So with no input from the hidden units, it relies on that basis and outputs near 1, which is symmetry detected, right? It has to balance out from somewhere. When you present an asymmetric pattern like 1 1 0 0, 1 0 0 1, at least one half sum doesn't balance. At least one hidden unit gets a non-zero net input and turns on. What does that do? It turns the output neuron off, right? Simple, like input, two layers, and then output. So, we have a two hidden layer network here with equal and opposite weights doing the job for us. If either detects asymmetry, the output flips to 0, right? The network had learned the concept of symmetry without being told. This is remarkable because a single line network can absolutely not do this. It's a higher dimension problem. The network wasn't given any hint about how to detect symmetry, yet through gradient descent, it found an elegant solution, right? Why does this matter? This example proves that hidden layers can learn meaningful features. The perceptron literally could not do this even in theory. With the backprop and a hidden layer, the network discovered feature detectors automatically. Let's try another example now, which is family relationships. The second example from this paper is even more impressive. This is the this is imagine two family trees where one is an English family, Alan, Brenda, Charles, etc., and one is an Italian family, Alessandro, Bianca, Carlo, etc. The family structures are identical, which means that they are isomorphic. So the structures are similar, it's just that the names are different. Okay. Examples. Sorry, the task first. Given two inputs, which is person A and relationship type, it predicts the person B. So person A and then relationship, like father, mother, like something. It will predict what the person B is. So, Saha and then father, it'll predict who that father is, or what the person is going to be. Examples: Colin, relationship may has mother, it'll give Margaret. Margaret has son, Colin. Penelope has aunt, then it'll give something like Diana or Emma if she has two aunts, right? There are 104 possible triples total in this example that is given in the paper. 104 combinations, which is people multiplied by the number of relationships they have. Remember, we were doing something like this just now, multiplying. The researchers trained on 100 of them and held out 4 as a test set. The network architecture. This was ambitious for 1986. The input layer are 36 units here, which is 24 units for person A, which will have 12 English and 12 Italian, and we'll have 12 units for relationships, which is 12 types. So what we are doing is English, Italian, and then relationship types, and we are training a network now. Okay, this is the input layer. Now we have layer 2, which is 6 units encoding person A. And then we have 6 units encoding relationship, which is learned compression. We have a third layer, which is 12 units again. One is the fusion layer, and the second is, where we have 12 units of the fusion layer, combining the person and relationship together. And then there's the layer 4, which is another hidden layer. For output, we get 24 units for person B. Okay. They used one hot encoding. This is a concept that you learn if you stick a little longer with ACM arc. We'll be going over this. It's a very important learning procedure that is used even today, and I learned it also this semester in my ML class, where exactly one input is on for the person, the exactly one for the relationship, and all others are zero, and it's the same for the output. Now, we went over the architecture and let's understand what the training and results were like. The training took about 1500 passes through 100 examples with a learning rate that decreased over time. So, the gradient descent. They also took a trick called weight decay, gradually shrinking weights to encourage the network to use just what's necessary, starving it. Result: the network generalized correctly to the four held out test triples. So the four test out triples, it was able to predict them, right? The testing. So this is also an example of segregating your database so that you can train and then test.
Yeah.
Uh, that's the key. It didn't just memorize the training data or fit, as we say, it learned the underlying structure of the family relationships, right? What did the hidden units learn? Here's where it gets really interesting. What we see is that the researchers analyzed the weights going from the input people to the first hidden layer, 6 unit person encoder. They visualized those weights and discovered interpretable features. Hidden unit 1, nationality. All English family members had positive weights. All Italian family members had negative weights. The network had learned to encode one hot encode, English versus Italian. But here's the cool part: most other hidden units ignored nationality. Why? Because the two families are isomorphic, the relationships are identical. So the network realized it could use the same code for corresponding individual across families. So it learned that it didn't need to reinvent the wheel here. Like two, they are separated and now we do that thing again. No. We use what we have identified as one thing because we have a bit for that.
Inside that category.
And then we use the other thing
Yeah.
again on a generalized thing, but when needed, we can reference it using the nationality one if needed, right? Like if I'm guessing an English person's relative, I don't even need to bother with Italian people's
Yeah.
names. So you can just use that as a segregator, right? And you can just think about that. Okay. The most hidden layers ignored nationality. Why? Because the two families are isomorphic, so the relationships are identical. The network realized it could use the same code for corresponding individuals across families. Hidden unit 2, the generation. Different weights depending on whether someone was in the grandparent generation, parent generation, or child generation. The network had learned to encode generational structure. So let's come to the final hidden unit. Family branch encoded which part of the family tree someone actually belonged to, like the paternal versus maternal side or primary branches. Other hidden units were also there, which encoded some additional features like gender, direct versus in-law relations, etc. Why this generalization worked? Because the hidden layer captured the true underlying structure. The fact that relationships are consistent across generations and families. The network could answer questions it had never seen. It's like network understood family semantically, not just memorizing facts. From the paper, the features captured by hidden units are not at all explicit in the input and output encodings because the hidden features capture the underlying structure of the task domain. The network generalizes correctly to the four triples on which it was not even trained. The power of distributed representations is clear from this. Notice that the people aren't represented by a single unit. Instead, each person is a pattern across 6 units. So a person is a function of 6 things. For example, Colin might be represented as high, generation 2, branch 3, whatever his attributes. Carlo, Colin's Italian equivalent, might be low. Remember, high was English and low was Italian. So low, generation 2, branch 3. Two things representing the same thing but on different, English and Italian, right? So this is what the labels are. There's like giving people rooms to a hotel, like key, and that key has different things attached to it. So based on these filters, you're like, oh, okay, building a section this, room number this, located next to the like trash composters. So if you want to find out all the rooms that have ever existed next to the trash composters, there's a like a key in that database that says next to trash composter, yes or no. Yes, query it, everything comes there. That has a, but this thing also has these attributes, right? So we are literally looking like, like at a database type structure over here too, like if you generalize or think like that. Awesome. They are similar but not identical, reflecting the nationality difference using high and low. This is called a distributed representation and it's incredibly powerful, right? Okay, let's see the aftermath. Then and now. What happened after 1986? The 1986 paper just exploded. Within a few years, backprop became the standard training method for all neural networks. 1987 from 1990 saw Jan LeCun, who independently discovered similar ideas, applied backprop to convolutional networks and recognized handwritten zip codes. This led to actual commercial systems reading bank checks, the first real world AI success in decades. A network called the NetTalk learned to read English text aloud. It started babbling and gradually learned intelligible speech. It was a media sensation. People applied neural networks to finance, robotics, speech recognition, and more. Between the 1990s and 2000s, progress slowed as the field hit scaling challenges, vanishing gradients in very deep networks, needs for lots and lots of data. Other methods like support vector machines became popular, but underneath, backprop kept improving, which was better activations, initialization schemas, regularization. Stay tuned because we'll be going over all of these. The deep learning revolution started in 2012, which is AlexNet, a deep convolutional network which won a major image recognition competition by a landslide. 2012, GPUs made training huge networks feasible, and suddenly backpropagation could start scaling again. And in today's world, we have every major AI system, it uses backpropagation. Convolutional networks are like the thing for vision now, CNNs, recurrent networks for sequences, transformers for language, and generative models for image and text creation. All of them rely on backpropagation or its variants. And here are some real world examples. When you unlock your phone with face recognition, backprop is trained on that network. Every time you, yeah, every time you essentially end up wearing a goofy thing and it's still able to recognize you a little, it changes its weights a little so that it can recognize you, right? um and it improves it. When you ask Siri a question, backprop trained those networks too. Whenever it makes a mistake but you give a feedback, that's what ChatGPT also does. Do you like it or do you not like it? You send it something like a thing that it will evaluate itself against, send a backprop, train it, and go again and give you another choice and then go back again. That's what it does. When you get a Netflix recommendation, backdrop train that model too. When you see content moderation on social media, it's a backdrop model trained the actual system. When you use an AI image generator, backdrop trained it too. Was it actually a dog, the image that you requested? Yes or no? And right, and you train it like that.
Yeah.
It all traces back to Rumelhart, Hinton, and Williams in 1986, the backprop paper. The Turing Award, something that ACM gives people out.
Yeah.
In 2018, Geoffrey Hinton, one of the three authors of this paper, Jan LeCun, and Joshua Bengio won the Turing Award, essentially the Nobel Prize of Computing, for their contributions to deep learning. The justification specifically mentions backpropagation as a foundation. Uh, intuitive designs and analogies that we can use to solidify all of the concepts that we just went through. Let me reinforce all of what we went through very quickly with some intuitions here. Okay, back propagations as error assignment. Imagine you're a manager at a company and the overall quarterly profit is down, right? You want to figure out which department is responsible and how much. Okay, you trace back. Sales department, their numbers were down 5%. Cost department, they overspent by 10%. Product quality, it only had 2% impact. Now you know where to focus the correction efforts essentially. Backpropagation does exactly this, but for neurons and weights. The profit is negative error, the departments are layers, and the responsibility is the gradient. Okay.
It's like learning from feedback is what background is.
100%, but a calculation associated with it. So you adjust the weight, and that's the learning, right? The hiker on a foggy mountain. When you're on a mountain in night in heavy fog, you can't see the valley, but you feel like the slope, is present under your feet, right? You can feel the slope. You take a small step downhill, then you feel the slope again, and then you take another step, and you repeat this thousands of times until you reach, right? If you just jump, then you don't know, you might like just fall down, right?
Yeah.
Like eventually you reach a valley, or at least a pretty low point, right, where you wanted to reach. That's gradient descent. The fog is high dimensional weight space, and your feet are the gradients computed by backpropagation. Each step is a weight update.
Yeah.
Feature learning as an abstraction now. The family tree example showed that hidden units can learn abstract features like nationality, which is a concept not given to the network, which is a concept which is not given to the network. Generation, another abstract concept that I just figured out on its own, and family branch, yet another one. This is how human learning actually works. We see raw data, individual family members and relationships, and build like mental models which are abstractions and concepts. Like this person has a soft spot for this person. This person gets upset if you upset this person. And we all know that grandmother definitely likes this cousin, a little more than she
Yeah.
likes everyone else, or something like that.
Yeah.
Or like these two like brothers have a fighting going on, so you don't want to mess with them too much. Like we have that like mental model that keeps adjusting itself all the time. Neural networks do something similar with hidden layers. These are our hidden layers and our like very high dimensional brain that we essentially live in, right?
Yeah.
Why does this depth matter? Because one hidden layer gave us symmetric detection. Five hidden layers enabled family relationship reasoning, right? Why? Because each layer can transform and abstract data even further. The first hidden layer might encode basic features like half pattern comparisons. Second layer builds on those patterns, like perhaps full pattern comparison. And by the time you reach the output, you have highly abstract compressed information, right? It's like how humans think: raw sensory input, low level features, higher level concepts, and then abstract reasoning, right? Some challenges and limitations to what we just went over, right?
Yeah.
Local minima. Our concern with gradient descent is you might get stuck in a local minimum, a valley that's not the lowest valley overall. So you're just there, but you can like and even lower, right?
Yeah.
This is like a mount, but like you want to go even more optimal, yeah. However, the 1986 paper noted that this rarely was a very big problem in practice, where modern research suggests that for large networks, most local minima are actually pretty good, nearly as good as the global optimum. Interestingly, adding more capacity, which is more weights, actually helps avoid bad local minima by providing alternative paths through the weight space. Training it like six times instead of just one, because remember randomly assigned initial weights.
Yeah.
If you do it random times with random places, you might find a different one which will eventually lead you to a lower minima, and then you'll be like, yeah, I found in five algorithms that this is the local minima, but one also led here.
Yeah.
And what I actually care about is the base local minima, or if that's what I actually care about, you can make a decision based on that. It's going to be different from network to network based, it depends on your use case, right?
Yeah.
Awesome. Vanishing gradients, that was another problem, where in very deep networks gradients can become exponentially small as you go backward through layers. This slows learning in early layers. Solutions developed in 1990s to 2000s were different activation functions, the ReLU activation functions.
I'll just like the gradient or something.
Yeah, better weight initialization, batch normalization. These are techniques
Yeah.
that make vanishing gradients not be a problem.
Yeah.
And residual connections. There were also data requirements which stalled things for a bit until 2012, which were neural networks, especially deep ones, need lots and lots of data to avoid overfitting. Overfitting is just rote memorization of something.
Mhm.
So it'll just like learn, and then be like, yeah, and it overfits itself. um they need a lot of data to avoid overfitting and make a lot of connections. This 1986 paper showed learning on relatively small data sets, which is for example 64 for symmetry, like 8-bit symmetry, 100 for family. Modern deep networks often need millions of examples, billions of examples. This is real practical constraint but not a fundamental limitation. It's a get good like problem, like there's also biological plausibility where some argue that back propagation isn't how real brains actually learn. The brain doesn't have a backward pass of the same structure, but the authors acknowledge this. They weren't claiming their algorithm is how neurons actually work. It's just that it's a successful learning procedure, and it's a little like it's a little similar, like obviously like it's not the thing, but it's a thing, right? The brain might implement something. Yeah, the brain might implement something equivalent or maybe something entirely different, but it's still an open question. Or not. We'll find out that in ARC, right? And let's come to like the actual takeaways, right? Let me tie all of this together in the next like 5 minutes, maybe. The three key insights from this paper are: problem was real. A single layer network could not solve these fundamental tasks like XOR or symmetry. Multi-layer networks could in practice, but nobody knew how to train them. And this had stalled neural network research for a decade. This was the second AI winter. First one, oh yeah, okay. Backpropagation was the actual solution for this. We use calculus, like the in the chain rule, to compute how much each weight contributed to the error. We propagate errors backward through the network, and then we update each weight proportionally to its contribution. Cool. There's also the third takeaway, which is it actually works. Networks learn meaningful internal representations. Hidden units became feature detectors like symmetry, nationality, and generation. Networks generalize to unseen examples, like literally out of thin air, because it just can. And the approach was general enough to scale to modern AI. Philosophical insight of this. After backpropagation, neural networks were just tuning parameters in a complex function. It wasn't clear that learning useful features was possible, but backpropagation ended up revealing something very beautiful, which is internal representations emerge naturally from the learning process. You don't need to handcraft any features, the network will literally invent them if you give it enough capacity and the right learning signal. And I believe that we are that, but on a very high dimension scale, like millions of years of evolution, if you know what I mean. Life itself is that, like, is what I believe, right? Like a complex, very high dimension neural network where neural can be replaced with whatever this network unit is supposed to be called, like thingle network, right? Like whatever. First coined here. uh the only competition is other gradient based models, which are just refinements of the same core idea, right? Your takeaway, what is your takeaway supposed to be from this? That back propagation is elegant because it solves a hard, well defined problem, which is the credit assignment in deep networks. How much weight to give to what? Does so with calculus, which is principled, not ad hoc, and very real. There is nothing wrong with calculus, I promise. Scales to systems with millions or billions of weights, enables networks to learn interpretable features which were not present earlier, and powers modern AI. I think those are good enough reasons for me to actually consider backpropagation IRL and learn it. If you take only one thing from this lecture, I'll say backprop is how deep learning works. It's not magic, but it is magic, and it's systematic gradient descent through a multi layer function. I'll say that again. It's not magic, it's systematic gradient descent through a multi-layer function, and it's a genuine breakthrough. My final words. Here's what I hope that you leave with. You now understand why the 1986 backprop paper mattered. Do you or do you not? Good stuff. It solved a problem that had confounded researchers for about 15 years. It opened the door to neural networks with hidden layers, and those networks, trained with backprop, became the foundation of every major AI system in the world. When you see a neural network trained on billions of examples, producing impressive results, image recognition, translation, text generation, remember, at the core, it's still doing backprop. Each weight updated by a small amount in the direction that reduces error. This is repeated billions of times. The elegance is in the simplicity of the core idea, combined with its power to solve hard, real world problems. This algorithm changed what machines could learn, and understanding it gives you a gateway into modern AI. I encourage you to tinker with this. If you want to build a neural network, understand what's happening under the hood. Is Backdrop doing the work? And if you want to contribute to the next frontier, know that backprop still reigns. Maybe your innovation will be the next big breakthrough that goes beyond it. But first, understand this one. Okay? Thank you for being here and taking the time to come here to actually learn about this paper, one of the most important papers ever like written. And there's also going to be an appendix that I share after we are done with this session today, which contains all of these examples, the script for today's like event, and it'll also contain a summary of all of the math that we did in a clean markdown style file for us to go over. Thank you so much for taking time to come to this session, and I hope to see you in the next session that we do together. And with that, I would like to end this session by saying just one small conclusion, which is backprop is equals to the gradient descent that we have plus the chain rule. A simple, powerful foundational like feature that has taken us from like honestly nothing to a perceptron, and from that idea of a perceptron to something that can actually form like intelligence like to some extent. And I think that will be the thing that is put together to create AGI, the general intelligence at one point. Generalizations, billions of them put together to create a general intelligence. But yeah, thank you for joining us. See you in the next ARC session.